people who can see recording later. Okay, so yesterday we left it at this point that when we put this filter there, there's a lot of issue. Actually, there should not be an issue when you put a filter there. The problem is this reverse conversion gain. Okay, so this reverse conversion gain should be a very small number. It should be a very small number. That was the major problem. So if I was putting here -10 or something, that's a problem. So I increased up to -40. So now everything makes sense. Okay, so if TOI is 21, then I'm expecting that the output power 1 dB compression point would be around 10 dBm, right? So that's what's going to happen. Okay, so the overall gain of this stage is 8 dB conversion gain, right? And there is a loss of around 0.1 here and 0.1 here, right? So that is a 0.2 dB loss here. So 8 minus 0.2, so that should be right 7.8, right? So the overall gain of this should come out to be 7.8. And if you do the simulation, you will find that, yeah, it is around 7.8, right? So this makes sense. Okay, so the culprit yesterday was this reverse conversion gain, right? It has to be a very small number, right? So what you communicate back to the input side, okay, that should be a small number, right? So that was the mistake here. And after that, everything is okay. Okay, so now we have this part. Now I will put in gain stages, right? So there are models again here. Okay, there is a very linear model. Well, it's a linear model here. Okay, this is called a variable gain. Okay, so if you go to system, algorithmic system, switch, and not here, maybe amps and mixer. Here you have this block. Now this block, okay, it doesn't have any compression characteristics. It has just a equation. It says that if V3, that is the voltage at this point, is basically 0 volts, then the gain of this stage is 30, right? And if V3 is basically 2 volts, then the gain is 0. So this is a variable gain stage, which is linear, right? And this is linear because at low power levels, I'm not expecting this stage to compress. So that's why this stage is linear. So let's go. Okay, F5 is to move this. So now this stage is linear. Okay, so you cannot expect any compression on this stage. Only thing is that this is going to be voltage dependent. So what I'm going to do is I'm going to put a voltage source here. Voltage source frequency domain. So I'm going to put here a voltage source. Okay, so if I put here 1 volt, for example, then it will be 30 minus 15, right? So equation is, you can put your own equation here, right? So this is a voltage dependent gain. So in circuits, you will replace this with a VGA, right? So let's say if I put here 0.5, then I'm expecting a gain of 22.5. So now there are no compression characteristics here. Okay, so if this is doing 10 dBm out, then this will be doing 10 plus 22 and a half, right? So 10 plus 22 and a half. So that would be compressing at around what? 32 and a half. That's what it's going to happen, right? So that's there. Let's give it a gain of 15. So now in this case, it is a linear stage, right? So this is not compressing. So 10 plus 15, so it will compress at 25, right? So this output would be 1 dB compression would be around 25. So here, I don't have to change anything. Okay, I'll just run the simulation and you are going to see 25 here. Okay, and it will be compressing, well, 1 dB compression. So basically 7.5 plus 7.5 plus 22.5. No, sorry, 15. Sorry, 15. Yeah, 7.5 plus 15. Okay, 15 plus 7 is basically 22. 15 plus 7 is 22. So 1 dB compression, 25, 24. So 1 dB is over here. Okay. it's able to put out 29. Okay, let's see. Again, the culprit would be this only. Okay, which is this. To start with, you started with 0 actually. So if it was 0, that was another story. Now let's say 7.5 over here and 15 over here. So it should be 22.5. It should be the gain. Rather, I'm getting 25, right? Okay, and then 10 dB compression plus 15. So it should be 25 dB compression, roughly around there. Okay, so we have put one stage which is linear. It's not doing anything of its own, right? Let's see if put this as 0, because I don't want to have this effect at all. 0 and 0. What it is going to do here? Even higher than that. Okay, so it should compress around 25. It should compress around 25. And what about the gain over here? Well, you can always plot everything at any spot, right? You can always write, powers at any spot. Okay, so we have added some voltage gain variation here. So if I declare, this is called tune. So if I tune this voltage, I would be able to look at what's happening over here, right? So if I change this, I can be changing the gain, right? So that's the variable gain amplifier, what it is doing, right? So if I put something like 1, so 15 plus 1, so 10 dBm, 10.5 dBm plus 15. Okay, so roughly we are in this range. Okay, so that's the story on gain and compression. Okay, now let's add a power amplifier. So let's add a power amplifier to this. Okay, so let's add a power amplifier to this. Okay. So I am going to put in again the same system in amplifier. Now, if I give an amplifier gain of, so what is the overall gain? 25. Okay. Let's say I want a gain of around 60, right? So there should be a 30 dB gain coming here on the PA. But then if you see, this is compressing at 25, 30 would be what? 55, right? So it will be compressing around there. So really, what has happened here is, if you can make a mixer that linear, then really it depends on this guy and this guy. It really depends on what power level you can deliver, right? So let's say I'm going to put here a gain of 20. Is there a question? Okay. Okay, so let's put this power amplifier. Okay, again, gain I will put here 20. Okay, and here over here I would put a return loss dB polar. Okay, and let's say minus 15, and dB polar minus 15, dB polar minus 15, minus 15, and return again I would put a dB polar here. Okay, and much higher than the gain, so let's say 40. And noise figure, if you want to include noise figure, 8. Okay, and then compression. Now here, this is compressing at 25. This has a gain of 20, so it should be around 45. If I don't want to see compression, I should be able to deliver 45 dBm, right? So that means that if I was to do 45, so this should be around 56, and this should be around 65. Okay, right? So now with the same inputs, I'm going to see the compression characteristics, right? So now the whole chain has a gain of roughly 45. What is this? dB polar. Okay, the problem here is not dB polar, is it? should be a small b, a small b, a small b here, and a small b here. Okay, fine. Okay, so now we are around 45. Okay, and we should be able to deliver 1 dB compression, 44, right? So if this is 45 point, so it is around 46.2. So let's go down 45.2. Okay, over here. Okay, so with this much of input, I am able to deliver 44 dBm out. So these numbers would make sense to you now. Okay, this is compressing at 10 dBm out. This is not at all compressing. It has a gain of around 15, right? So if this is 10, then this is 15, this is 25, and then plus 20. So that would be 45. So basically, this would be compressing around 45 something, right? So that's what it is doing. It is compressing around 45, right? So 44 or 45 is these numbers are going to be nearby because we are fixing with TOI, right? Okay. So now this chain makes sense in terms of gain and in terms of compression, in terms of power delivered. Okay, so now what we are doing is we have a chain here. Now we want to analyze this chain. Now what is going to be restricting you to deliver so much of power is the compression on this guy and the compression on this guy. Okay, because there is no other place there is a compression, right? So it's this one or this one, right? So usually this is the problem. Okay, why this is a problem? Because you should look at how do I make a up conversion mixer. Okay, so this is going to be some form of a Gilbert cell mixer. Okay, so how does a Gilbert cell mixer work? Okay, so let's see how a Gilbert cell mixer works. Okay, so that's one thing. Now there are other mixers also. Okay, so there are two more mixers I would mention here. Okay, one would be your balanced diode mixer, which is a passive in the sense that it uses diodes, but it doesn't give a conversion gain. It is going to give you a conversion loss. And the topology for that is going to be, I'll show you what this design for a double balanced mixer is. But right now I'm going to show you what is a Gilbert cell mixer here and what are the constraints, okay, in a circuit. Okay, so let me open Gilbert cell mixer over here. Let's open a presentation. Sorry, trainings. Okay, Gilbert cell, this one. Okay, so let me show you what is a Gilbert cell, and then later I'll show you in circuit what is a Gilbert cell. Smith chart, Gilbert cell, way down. Oh, not over here. Just 1 second. Bear with me for a second. On this one. Okay. Gilbert cell. Okay, over here. Okay, so there are two circuit, well, two same topologies are there. Okay, one is using a bipolar. One is using a bipolar. Other one is using a FAT, right? And then so this basic topology is using some form of a cell like this, okay, or like this, right? So what is that cell? Okay. Okay, so if I look at this cell, so how is it working? How is it working? It's working this way. M1, M2, okay, they are going to pull some current depending on this signal Vx. Okay, so if this signal Vx is positive or negative, right? So it's a differential signal, right? It can go either way around the bias. It can go either way. So if it is positive or negative, that decides basically what is I1 and I2. That I1 and I2 basically is controlling what's the gain of this cell or the gain of this cell, right? And then with that gain, you are going to multiply the signal Vy. So it turns out to be a multiplication, because in one case it is the GM of these differential stages. So there are basically 3 translinear cells. So what you call this is a translinear cell. Okay, so there are 3 translinear cells. Okay, 2 at the top and 2 at the bottom. 2 at the bottom are steering the current and controlling the GM of these devices, M3, M4, M5, M6. They are controlling GM of the device, right? And then Vy is basically multiplied by the GM of the device to result in a current here. So basically the current here is proportional to the multiplication of Vy and Vx, right? And if I do that, I can just multiply with RC. That will give me a output voltage, correct? So that's how I get a multiplication of 2 signals. One signal is varying the GM of the translinear cell. Then the other signal is basically GM-RO is the gain of that stage. So GM is varied with Vx. So GM is a function of Vx. And then RO is going to be RC. Okay, so that will be the voltage gain multiplied by the input Vy. That will be the output. So basically the 2 voltages get multiplied. So now this is a multiplier, which is as good as a mixer. Now, what is the, so you can do the maths here. So if you see the connection this way, it is I7, I8. Okay, a part of this is drawn in here, a part of this is drawn over here. Again, I8, I6 is drawn over here, and I4 is drawn over here. So if I do this, total differential output current is I out is I7 minus I8, which can be expressed as sum of the 2 voltages, because I7 is I3 plus I5, I8 is I4 plus I6. So that's there. I have rearranged the terms. And then for this translinear cell, okay, this difference of current, right, that equation I place in there. Okay, and after that I simplify it. So after simplifying, so this is a bipolar. In case of this, you will understand. So after I simplify del out, I multiply this RC. Now, 2 things can happen. One is K. K is basically mu n Cx W by L. Now, this K is going to be same if all these transistors are going to be same. Now, if the transistors on the top are K1, that is, they have a different W by L, and this is K2, then the relation is basically square root of geometric mean of roughly K1, K2 times of square root of 2 times of Vx, Vy. And if you multiply with RC, you will get the conversion gain. Actually, you will get the output, and then divide by Vy, you will get the conversion gain. So that's what's happening. Now, what is important here to know is that the input voltage range, okay, is root 2 times of V overdrive. Okay, so basically it means, so let me show you a curve. Can I? Okay, yeah, here, a curve. Okay, so consider only one curve, one blue curve and one red curve. I am going to sweep input voltage here, okay, Vy, okay, from negative value to a positive value, right? And then this is the current I am plotting. So what is going to happen? The current is going to steer in a translinear cell. So for example, let's pick up any translinear cell. So this is a translinear cell, right? Okay, so here, what is going to happen is if I change Vi1 minus Vi2, that's a differential input. If I change that, then I'm steering this ID1 and ID2. So if I plot ID1 and ID2, so one of the current is going to drop, the other current is going to increase, because the summation is going to be the total tail current. So this is called the tail current. The summation of the current is a constant. So this is a DC current, right? It is a constant. So one of the currents is going to decline, the other current is going to pick up depending on what is the input. Now, this is the range which can be considered as a linear range, because if you have a voltage, input voltage, then the output voltage will be this current multiplied by the RC or the load, right? So the total output voltage is going to be this current multiplied by the load. So now you can see that there is a linear region here, okay? That linear region is bound by plus minus square root of V overdrive, Okay, so plus minus square root of V overdrive is the linear region for a mixer. Okay, so now what does it say? It says that if my input goes beyond this range, then the mixer is going to compress, right? Okay, so that means that if you want to adjust the compression point of a mixer, you have to work with the overdrive. Okay, so you have to work with the overdrive. And what is the overdrive? Overdrive is square root of I tail, right, divided by mu n COX W by L, square root of. So I can write it over here. Let's say I will write it over here in the insert equation. Okay, so basically input range, right? So overdrive. Okay, so I'll write overdrive. So V overdrive will be equal to, okay, so V overdrive will be equal to twice of the current. So the twice of the drain current. So twice of the drain current is the tail current. So basically, if I assume this is a tail current under no signal, then ID1 equal to ID2. So basically ID1 equal to ID2 will be equal to half of the tail current if there is no input signal. So basically twice of ID, which is again tail current only. Okay, so that will be square root of, okay, so let me go here. Okay, what happened here? Okay, so this thing is going to be equal to, okay, equal to square root of some fraction, which will be tail current, I tail, divided by, so I can put I tail as that. So don't worry, so you don't want to get confused. So this will be I tail, which is twice of I drain, okay, divided by mu n COX. So that will be mu n COX, and then I would put a bracket here, W by L. Okay, so this will be mu n. This is an n-channel device. COX is basically the gate capacitance. Okay, mu n COX. So this has gone out. Okay, hang on. Okay, so here I would do a W by L. Okay, so now my question is, if I want to increase the input voltage range, I want to increase overdrive. So one option to me is I increase the tail current. Okay, now if I increase the tail current, one more thing is going to happen. The resistor which I put here, okay, they have to be less. Otherwise, these transistors which are below these resistors, they will run out of the voltage. Okay, so once they run out of the voltage, okay, then this whole maths is wrong, right? This whole maths is wrong. Okay, so you have to keep all the transistors in saturation. That's why you should have a sufficient voltage at these nodes. If I increase the tail current, then these resistors have to be reduced. So this thing you should have in mind, nothing else. Okay, so now I can increase the overdrive voltage by increasing the tail current, but then I have to reduce the load resistance. Okay, so you have to be clear that as soon as you do that, okay, so this is a square root relationship. While the gain is a I tail into RDC, or not I tail, actually, it should be difference delta I into RDC, right? So now, if I change tail current, so it is going to affect overdrive with a square root of I, while it is going to affect the gain directly, as I tail is proportional, the gain is proportional to I tail, while the overdrive is proportional to square root of I tail. So if I use I tail to improve the input voltage range, or rather the compression characteristics, okay, then I tail has a problem, because the gain is directly affected by I tail, while the overdrive voltage is affected by square root of I tail. So that's not a good procedure to do that. The other would be if I reduce W by L. So this is going to be a good way of doing it. If I make these transistors is small, Okay, so if these transistors are small, then the input voltage range, which is plus minus √2 of V overdrive, that is going to be large, right? But then this doesn't come at the expense. This also comes at the expense of gain. So if the slope of this curve is the gain, right? It is going to be the slope of this curve is going to decide the gain. So if you increase the input voltage range, okay, you are anyways, okay, recording is started. Okay, so if you increase the input voltage range, okay, anyways, your gain is going to drop because you are operating from a certain tail current, right? So this curve has a lesser gain than this curve, right? Okay, so conversion gain is going to be sacrificed anyways, whether it is I tail or W by L. Okay, you are working with V overdrive. You are increasing V overdrive. Okay, so you will be doing this at the expense of conversion gain. So you should be able to design a mixer, okay, with a very high compression point. The input voltage can be plus minus √2 of V overdrive. So V overdrive can be really large if I use small transistors or if I use high tail current. Okay, so having said that, you know what is the trade-off here in Gilbert cell. Trade-off here is you are going to trade off conversion gain with the what you call input voltage range. Okay, so that over here in system, you should know that if I put a conversion gain of 8, okay, in this model, there is no issue. But when you put here a Gilbert cell, okay, then you should know it is the tail current and it is the size of the transistors which is deciding the compression characteristics. Now let us see when the mixer is totally compressed, what is the problem? Okay, so when you compress the mixer, what's going to happen? Okay, so when you completely compress the mixer, right? So what is going to happen in this topology is these will start acting as switches. Okay, so either there will be a complete lack of I3 or there will be a complete lack of I6. Okay, so basically these transistors, they are no longer what you call voltage controlled current source. They are not operating in linear region. Okay, they start operating like a switch. Okay, so when you compress this, okay, then at that point, these TN3, TN4, TN5, TN6, they are just doing current steering. They are just switches. They are no longer transistors as we see it as a gain stage, right? So this is GM, this thing, right? Now, same thing is over here, right? Now, once this becomes a switch, once TN1, TN2 becomes a switch, then what's going to happen? Either I1 will be 0 or I1 will be I tail. Okay. Okay. Is it easy to implement the Gilbert cell using CMOS in sub 100 nanometer node? Okay. We are scaling threshold voltages also with the supply voltages. So there should not be a problem because then the overall voltage scheme will come down. See, VDD will go down to, let's say, sub 1 volt, right? So threshold voltages are scaled to like 0.15, 0.2, right? So it really is not going to hurt you because you are scaling VT also with this, right? The problem is the leakage, right? So that's the problem. Okay, so I hope I have answered your question here. Okay, now coming back here, if I1 and I2 are just steering rather than TN1, TN2 as a gain stage, then the question is either the GM is 0 or the GM is going to be maximum. Now, what does it mean? It means that the conversion gain has a control of allo for a certain power level. But after a certain power level, the lower transistors will start acting as switches. So now you cannot boost the conversion gain with this one. So you understand? So you could boost the conversion gain with allo to a certain extent. So allo power can be increased and the gain will go up for the mixer. But beyond certain point, the lower transistors will start acting as switch. So no longer the allo has a gain over control over the conversion gain. Okay, so what it means is this allo power can not be boosted to any level and keep on increasing the conversion gain. It's not going to happen. Okay, so at some point the gain would be saturated for the lower stages. At some point, the gain would be saturated for the upper stages. So the upper stage saturation you are seeing as a compression. Okay, and the lower stage is basically is going to, beyond a certain point, allo power is not going to affect you. Okay, so in a real mixer, that's what happens. Now, a multiplier versus a mixer. Okay, you should know that multiplier is nothing but a mixer only, but it is completely linear. So what's the difference? You are operating the multiplier in the linear range. So it's a 4-quadrant multiplier. Okay, why 4-quadrant? Because both Vx and Vi can go positive and negative. So it's a 4-quadrant multiplier. So if you operate a mixer in this input voltage range, it's a multiplier, not a mixer. Okay, if you are going to basically keep on bumping the power till the transistors, they start acting as switch, that would be a mixer. Okay, and in that case, the lots of harmonics will be generated. Now what will happen is that the even harmonics will be canceling out. Odd harmonics will not be canceling out. Okay, so you should know this is a differential. And even mode means that VO is not going to see those harmonics, but odd mode means you are going to see those harmonics. So in a mixer, if it is a balanced mixer, if these transistors are really good, matched well, then even harmonics will not be a problem. Odd harmonics will be a problem. Okay, so what happens in case of a communication system is, if you operate these mixers like, with a very high conversion gain, if you operate these mixers with very high conversion gain, what's going to happen? Okay, you are going to put out a lot of harmonics into our chain. Okay, so this is our chain. So if you are going to put out lots of harmonics in a communication system, what is going to happen is, anywhere else, if there is a mixing involved, those components would come back to your IF or your frequency of interest. Okay, because everything folds. Okay, whenever I do up conversion, okay, the frequencies fold over each other. Okay, so if you put harmonics into the chain, what's going to happen is, due to some non-linearity of this amplifier, those components will come back. Now the question is, that is welcome, but if they come back in kind of a distorted phase, that's not welcome. Okay, then people start doing like harmonic suppression on this. So they will put attenuator pads here, they'll put attenuator. That's a band-aid solution. That's because you didn't design it properly. Okay, so a mixer and a chain would not need some kind of attenuation pads. Old guys used to do this. They would put attenuation pads everywhere, and then they would minimize leakage components using attenuation pads. Now if you design the mixer to be well balanced, okay, then even harmonics is not an issue. It's odd harmonics which is the issue. Okay, so this, as a designer, you should take into consideration. So this is all input I'm going to give you on this one. Now we are here. Now what we are going to do is, we are going to replace this with what you call a 2-terminal device, right? So instead of using this mixer, I'm going to use a mixer with same characteristics. These numbers are going to be same, but I'm going to use mixer with allo. Okay, so there is a mixer with allo here. System. That's this mixer with allo. Now, why am I doing this? Okay, because the budget analysis which you do here. So if you go to simulation, you will see something called budget. Okay, so the way this is done, okay, it is assuming that all the components are going to have 2 terminals only. So now this guy has 3 terminals, and even this one has 3 terminals. That means that I cannot use this chain for budget analysis. So for budget analysis, what do I have to do? I have to go here and change this. I'll have to define an equivalent mixer here, which is 50 ohm. I am expecting RF plus allo. Okay, just one second. Sorry for the gap. Okay, so let's come back to here. So now here I can choose either of the sidebands or I can choose standard. Okay, so I can choose the standard or either of the sidebands. I can put a conversion gain of 8 as we had, and then I can put the return loss as dB polar minus 15 or minus 10, whatever we were putting there. Okay, and this one would be minus 10. So there are only 2 terminals here now, no 3 terminals. Okay, and then you can put a noise figure, let's say of, actually this will be large, right? So let's say 4. And here TOI as well. If I put a very large number, it means that this is linear, but this is not linear, right? So SOI was 30 and TOI was 21. And next is the LO frequency. Okay, so LO frequency is going to be just LO, as we were doing, LO in gigahertz. Okay, so now this is the equivalent of that. I can throw this off. Okay, I can replace it with this guy. So that's all set. I can still repeat the simulation. And what? Conversion gain is 8. Huh? This doesn't make sense. This is 8. This is 15. And this is going to be 20. So what happened over here? It should not make a difference. This is 8 dB gain. This is 1 volt. So that means this is a 15 dB gain. And this is 8 plus 15 is 23 plus 20 dB gain here. That is not making sense unless frequency is LO. LO is 27. This is 27.6. This is up conversion. Okay, let's build this again. So, you know, I usually don't see this, but let's do this again. Let's see, we are over here. Okay, let's see what happened over here. Okay, so this is a conversion gain of 7.7, which we are expecting, right? So there's nothing wrong over here. Okay, so after that, I placed a gain stage, right? So let me put a gain stage. So let's enable this one. Okay, so I'm going to enable this here. So what happened over here would be this guy. And if I do simulation now, this Y, hang on, why is this the culprit? There is no frequency dependence on this. Why would this be the culprit? It doesn't make sense. This is V3 into I. This should not be a culprit. These are all ideal components. This should not be a culprit. Anyways, I am not sure. I'll have to do debugging. But anyways, I was going to replace this anyways. Okay, so I will put here another gain stage. So I will figure out why this is happening. Yesterday also something happened like that, right? Conversion gain of 8. So if I put here a gain of 15, as we were saying, 15, and this compression should be around, so this is around what, 10. So this will be around 25, 35, 36 should be TOI here. And then 36 plus 9 is 45 should be over here. So there is something with the model. Okay, so now it is 25. So now this makes sense. Okay, So now this is compressing at 25.5, 24.5. Let's see, 24.5, 24.5. Okay, at this point, it is putting out 24 dBm, and then I have the power stage. Okay, so somehow that ideal VGA was an issue. I am not sure why it was an issue. I have to figure this out. And then there is a PA here. Okay, so now I have actually skipped what happened over here, but I'll address this. Okay, sometime I'll address this, don't worry. I don't see a problem for that to be happening. Okay, because according to me, everything is okay over here. So now this should be around 45. Okay, 45 point something, 46.4, 45.4, 5.4. Okay, so basically over here it is delivering 42. Now it is supposed to deliver 44. So maybe this one is compressing, maybe this one is compressing. So now this is a specimen. Okay, this chain is a specimen for budget analysis, and want to see how is the compression going for the chain. Okay, so how would I put the budget analysis together? So I'll go to my presentation. Okay, I'll go to my presentation. Don't say. Okay, I'll go to my presentation here. So we are over here. So we have some chain like this. Okay, and I am also putting one more BPF here. Okay, so now, okay, so see here, I have a TOI, so I have 6 and 2, right? So that means that my compression was around roughly around -10. So right now what chain I have put here, the compression is around +10. Okay, so that's the difference you should understand here. Okay, and then I have a filter, a gain stage, and so if this is 26, so it will be 36 and 42. So basically, if you do not want to see a compression, it should be 36 and 42 for my case, because I'm designing for 10 dB higher, 36 and 42, so roughly like that. So that's how I keep account of compression, is using TOIs and SOIs, right? And this guy is compressing most probably. Okay, so we will see this when we do the budget analysis. We will see that this guy is compressing. Okay, so to do the budget analysis, okay, all you have to do is you prepare this, and you know where is your compression. Okay, and you just put here budget controller, right? And that's it. I don't need a current source here. I just need a V out here and a terminal. The terminal, I can put here a terminal here. And then all I need is, we have the chain, right? So this is not going to do a harmonic balance. This is going to do a budget analysis, right? So let's do that. Okay. So let's go here. I don't need a harmonic balance here. Okay. I don't need even these. Okay, I don't need this. Maybe I'll change this with the terminal. So if I go to simulation as parameter, it doesn't matter actually. Simulation as parameter, terminal. This is a 50 ohm terminal, right? So I have this chain. If I want, I can put another filter here, which I'll do later on. And then I am going to put here what you call the budget controller. So if we go to simulation, budget analysis, right? And take this, and that's there. Okay, so now setting this up. Okay, so I'm going to just follow what I have over here. You can read why they are there like that. Okay, here you have to be careful that this is going to do iterations of power so as to determine compression of each stage. So you have to put a big power number here, right? Okay, so I'm going to take 5th order. Okay, frequency span for noise simulation. So this would be like channel bandwidth. Okay, this should be like a channel bandwidth. So let's see over here. Okay, so noise span, I'm going to do per hertz computation, right? Then over the channel bandwidth, I have to put a resolution. So this is for integration of power. Okay, so 1.25 megahertz, for example. You can put kilohertz also. It depends on the spectrum you are going to integrate power. So you are going to integrate power of, so this is your resolution bandwidth. Same thing as in your spectrum analyzer, right? You have a resolution bandwidth. Something similar is there, right? So that's there. So you have a resolution bandwidth here. Components in rows and columns. Okay, there's no question, right? There is a person to be admitted. Fine. Okay, so this is all fine. Auto format, yes. And I am going to do rows. Angles are in degrees. Frequency is in hertz. And this max component input power, I'm going to put 40 because, you know, the other chain was compressing 10 dB earlier, right? So in this example, this was 10 dB earlier because of the mixer, right? So I have to go up to a higher compression power so that it is going to iterate the power and see where the compression of each stage is. Then I'm going to add the measurements. Okay, so what measurements I want to do here, right? So basically, what am I going to do? I'm going to look at output gain change. So that will give you compression. So if I go to output gain change, P gain change. So this is going to give you compression characteristics. Next, let's see what is next. The next is gain. So I want to do the gain budgeting. So output gain. Power gain, output gain. So that was gain change. This is gain. Okay. So next, what I want to see in the budget, I want to see component output P1 dB and component output SOI and TOI. Okay, right? Okay, so I want to look at P1 dB of each component and TOI and SOI. Okay, SOI and TOI. Okay, so here I am almost ready with my budget simulation, right? So what it is going to give you? It is going to give you, let me just go here. I have to fix the input power. Okay, so you are not going to do it over a variable power, right? So if I look at this curve, okay, let's say I want to analyze it over here. Okay, I'm not going to see any compressions here, right? So if I go to 1 dB compression point, that would be at an input power of, so basically 46, right? 46.5, 45.5 over here, minus 3.6. So that's my input power, minus 3.6, right? So over here, if you can see, I'll put here a particular power where I'm going to look at it, right? I'm going to look at it at a particular power level, okay? And there, here, why am I sweeping this? Should not sweep it. I want to look at a particular power level. So I'm not going to sweep it. If I sweep it, I'll have to look at the index n. Okay, so if you remember, we were putting index n to find out at any point. So let's find. Okay, you should not be sweeping it. So let's put at minus 3.6, or rather put here as minus 3.6 and not sweep it. So we are not sweeping it. Over here, I'm going to put a power of minus 3.6. Minus 3.6. Now this is going to be a compression, right? And power sweep is not over here. So there is no way you are going to see power here. So this is doing its own sweep. Okay, and it will spit out a number. And if I hit simulate, Okay, what does it say? Okay, so now these problems you should be able to take care of. So the problem it is referring to is noise, yes, temperature. I'm going to do it at absolute 0. And let's now do this. So it says magnitude S22 is greater than 1, but must be less than 1. So that's the mixer here, maybe. Which one? S21, S11, S21, S11. Where is this warning coming from? Mixer 2, S22, 10, greater than 1, must be less than or equal to 1. So basically it is complaining about S22 here. Ah, why would it complain? Should not. If it is this also, it should not complain, right? Unless it is interpreting it as a positive number. See, it is interpreting as a positive number. Okay, so this angle is 0. Forward coefficients. Oh, do you think it should give it is 10? I don't think so. If you go to the help, dp polar, xy, complex value, polar. Oh, they are in this model putting a positive number, and that's assuming it to be negative. That's kind of weird. SP1 and SP22. 1, 1 and 2, 2 is greater than 0. Greater than 0 means they are assuming a positive number over here. Come on. So these conventions you should read. This is a return loss. dB polar. That's the problem. If I do a dB polar, there is no issue with this. dB polar minus 10. Okay, understood. Okay, there is no issue with this. Okay, done. Okay, so now this budget analysis is done. It doesn't have any warnings here. Everything looks fine. Now let's start looking at this thing. Okay, compression. Okay, so it is saying that at that power level, LPF is not compressing. Mixer is compressing by 0.194. BPF, this is going to be a loss actually. This will not be, because you should see as a delta. Okay, so for example, here 0, here minus 1.94. So these are at the outputs of these components. Okay, outputs of these components. So at the output of a mixer, I don't see, I see there is a gain of this, which will be, gain change would be 0 on this roughly. Okay, next is mixer. At the output of a mixer, I have gone through a gain change of 0.19. So means that the mixer is compressing 0.19. Next, sorry. Next, from mixer to the output of BPF. Okay, over here, over at this point. At this point, this filter is not contributing anything to the compression, right? So the gain change contributed by this is 0, right? So this is like a cascaded stuff, right? So let's go here. Okay, so here you are seeing minus 1.94. Okay, so it has remained same. Now amplifier 3, I have gone from 0.194 to 0.397. Okay, so let me, oh, I lost the previous one. So here I am going through another 0.2 dB compression here. right? Now going to amplifier, I'm going from 0.397 to 0.58. So here, this is compressing, this PA is going to compress by that much. So let me just do one more thing before I do this. I can always cancel this and I can put back my previous things, okay? I can put back my harmonic balance. I can put back my harmonic balance. Here, I will put two frequencies as IF and say apply. And then we are going to put here LO and say add. Okay, so that's what this was. And I was sweeping IF power over here. IF. And I was sweeping from, let's say, -20 to, let's say, 5. Okay, 0.2. Okay, fine. So I'm doing a sweep here, and then I was doing the computation for powers, right? I have got rid of that, but I can copy it from another place. So if I go to two-tone, I can copy from here, if you remember. And I'll put back all the things here. Okay, so let's get rid of stuff. P out is half real of that. P1 is gone. P2 is gone. P1 dBm is fine. This is gone. 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 And this is gone. So only 3 equations. And here I was looking at an index of 10. That's my desired component. No, not here. I will not do it here. I will do it here. I'm going to look at the index of 10. Okay. So I'll be out in dBm at the index of 10, and then this is the gain. So that's fine. So we are back to where we were. Okay, so these variations are fine. So let me just simulate this again. So that's fine. It's not there. Let's look at what's happening here. I out is not there. Okay, let me put it back. Okay, probe components, I out. Okay, fine. Cannot resolve RF power. Okay, of course, this is IF power, not IRF power. This is IF power. This is IF power, not IRF power. Okay, fine. Okay, so we are over here. We were doing gain compression. Okay, so the gain was doing like this. Okay, so let's see at -3.6 where we were. Let's put out a P out dBm. Okay, and let's put here the gain. Okay, so we start with, see now, you can see what happened. That's why I repeated it. The reason I repeated it was here, I was not putting dB polar, I was putting polar. So it was regarding this as a positive number. So that was why we had absurd numbers here. Okay, now I have corrected that. I have repeated the simulation and I have a gain of 43. Okay, and 43.1, 42.1, 42.1, which happens at -1. So basically I have to put here -1. That's why I repeated it. So don't worry about it. I'm going to cancel this one. I'm going to cancel this one. And I am going to enable this one again. Enable this one again. Okay. Now I'm going to do at a 1 dB compression. Okay. At a 1 dB compression of input is -1. So at that point, I'm going to do this budget analysis, right? So other than this, I don't know if it'll complain about this one. Yeah, it is complaining about this one. So let's short this out and fine. Oh, it doesn't even like that. Okay, fine. Now it will not complain. Okay, so now you are seeing a 1 dB compression, right? Okay, you see now, because earlier we goofed up with the mixer with the return loss. We corrected that. Now we are having right number. So now at -1 in, the whole chain is compressing by 1 dB, and I want to see the contribution of compression from each one. right? So this I can see in this table. Okay, so that means that the mixer is compressing by 0.35, right? And then LPFs and BPFs are doing nothing. Then amplifier, the driver amplifier is compressing by 0.7. Okay, so 0.7 over here, 0.35. So the driver is compressing by the difference of this, which is again 0.35. So basically this guy is compressing 0.35. This guy is also compressing around 0.3. Okay, and this guy is compressing around 0.3 again here. 0.3, 0.75, right? So 0.3, 0.35, and 0.35. So roughly 0.3, yeah, 0.35, 0.35, and 0.3. So the total compression is around 1 dB, correct? So that's the total compression. And what is the output power, right? Output power is 42.11. So this is a 1 dB compression point actually. Output gain, yeah. So 1 dB compressed gain is around 42.11, right? So the gain contribution from the mixer is 8. Then this is doing nothing. Then the amplifier is doing a 22.5 gain, but it is compressing by 0.35. So you see 22.2 or 22 point something. And then the PA is compressing by another 0.3. So 40, the whole gain is compressing by, okay, PX compressing by point this thing. So this is a cumulative gain here. This is a cumulative gauge change here. So whenever you read the numbers on a component, you should see the difference going from one component to another. Now, what is over here? P1 dB. Okay, so P1 dB of mixer is 10.5. So individual simulation, it shows 10.5, right? So that's over here. Then over here, it was 25.4. And over here, it is 45. So basically, all these different stages component-wise. So this is a cumulative number. So these are cumulative numbers. So you should read them as differences. Well, this is a component to component number. So the compression points, the 1 dB compression points are over here. For a mixer, it is 10.5. For the driver, it is at 25.5. And for power stage, it is around 45.5. Okay, and then these are your SOIs and these are your TOIs. For mixer, I put a TOI of 21. For driver, 36. For power stage, 56. And similarly, component-wise, SOI is 30, 45, and 65. So that's what we placed here. Okay, so you can do a budget analysis like this. You can look at the linearity, right? How much they are compressing and all that. So that's all about budget analysis. Now, same thing you can carry out. Same thing you can carry out on a receiver chain. So by this time, what is the takeaway from this exercise? The takeaway is the following. When you put together this chain, okay, what you do is you should know what should be the power delivered. So you should start from here. Okay, not from here. We started from here. Okay, that's a wrong thing to do. On a receiver, you start from here. But from the point of view of a chain, you should start from here. So let's say if I want to deliver, how would I modify this chain? Okay, let's say I want to deliver 1 watt. Okay, so I should start from here, not from there. If I start from there, that would be like a receiver. If I start from here, that will be like a transmitter. Okay, so transmitter, I should start with the power delivered. So let's say I want to deliver 1 watt power. So in this case, it will be 42. 1 watt power would be 42, right? And then 1 watt means 30 plus 12, right? Plus 9. So that will be 51. So now it will deliver 30 dBm. Then this has a gain of 20, right? So you just bring these numbers down by 20. So if this is 42, then minus 20 will be 22 over here. Okay, and this 51, 20 down will be 31 over here. So now what this one can do? This one can deliver 10 dBm. And then a gain of 20 on it. So this one will deliver 30. So that's how you build the chain for transmitter. Not from the input side. I started the wrong way. Start from the output side, the output power delivered, right? So linear power, let's say 1 dB compression is around 30. So I start doing my my planning from the output side. Then this is 10. This has a gain of 22.5. So this should be minus 12, right? So minus 12. So basically that means that this should be around 0 or 2, right? So let's say if I put here 2, and then this would be around, let's say 2 plus 9, that would be around 11, right? So you'll be over here. Now this chain is for 30 dBm out. Okay, so now I cross this, I enable this guy again, and put here a probe, I out. Okay, I'm going to put here I out. Okay, so now I have constructed this, instead of 45, I have constructed this for 30 dBm out. And where would it happen? You have to first do a sweep, power sweep, which I'm doing over here. And I will go from minus 40 to minus 5, because I have gone down by 10 dB, right? Okay. And I'm going to run this simulation again. That's fine. This would go off because I'm not doing budget analysis. Over here, I can put gain. Okay, so gain is around 43, and I'm going to put P out, right? And what am I going to look at? I'm going to put a marker here. So over here, it's a gain of 43.1. So let's look at 42.1. Sorry, 42.1 over here. Why is it delivering 24 dBm out? This is 30. So that means 42 and 51. Then minus 20, 22, minus 20. So this will be, it should be delivering 10. So 22 and 31. Then this guy, conversion gain of, so 22 subtract from 10 minus 22.5. Okay, so that will be 12 minus 12.5 minus 12.5. So this is good enough. Okay, let's do the budget. We will come to know what has happened here. Okay, it should deliver 23. Sorry, 30. It should deliver 30. It's not delivering 30. So let's see who is the culprit. Okay, so I will cross this one, across this one. I will bring this out. Cross this one. I will short this one, and I will enable budget analysis. And this is guy is compressing. It is compressing at around minus 17 itself. I always see this as a problem. Minus 17 itself. Let's run this. Okay, hang on. I did a mistake. Minus 17, right? Why it is compressing? Okay. So 1 dB compression is around minus 17, and mixer is compressing by 0.7. So this is the mixer which is compressing, and then PA is 0.1. So the culprit is the mixer, right? Culprit is the mixer. Why should it be like that? Is this a, what is the gain on this stage? 15 dB. Okay, 15 dB is the gain on this stage. Okay, so I was considering 22, wrong. So it will be like 10 minus 15. 10 minus 15 is going to be minus 5. Minus 5 means plus 11 on it. Minus 5 plus 11. Minus 5 plus 11 is going to be 6 or 7. Let's put here 7 or 8, 7. And then this should be around 20, 7, 17, 18. This should be around 18. So now, if I boost the power up again, okay. So now it should be if I boost this power up again, minus 12. Okay. Okay, 1.9 dB compressed. Again, the mixer is 0.7 dB compressed. Okay, 0.5, 0.5. Okay, 0.7 dB compressed mixer. Okay, 10, 20. So now mixer is 0.35 compressed now, right? Now the amplifier is 0.6 compressed. Okay, so let's look at what is the power delivered. Okay, P1 dB is around 31. So it should be able to deliver power. Okay, so the mistake again I did was I'm assuming 22.5 gain. It was 15 gain. Okay, so that was the problem computing this guy. Okay, let's go back and do this again as this. Okay, and let's put this back here and do a canceling out. Let's do the sweep again. Okay, so this will go off. I am looking at gain and I'm looking at P out. Okay, so now is it delivering 31? Let's see. So we start at 43.1. I'm going to look at 42.1. Okay, still it's delivering 28. Okay, so now you have to see which one is compressing. So basically what this is this is allowing you to do back and forth. And while if you construct this and there is no notorious character over here, and if you do everything right, then you would not have to do this. You would not need to do a back and forth. Okay, so let's do this again. Okay, so let's look at 1.6 dB compression is there. 0.7 dB is coming from the amp 3. Okay, so 0.7 dB is coming from amp 3. Okay, so basically that means that I have to bump this up, let's say by another 2 dB here. Okay, and run this again. Still I see this is compressing by 0.7. Okay, sorry. Okay, so now this is 0.35, the original situation. But over here, this is going to be a compression of 0.5. So this guy is compressing 0.5. Okay, so let's change this a little bit up. Okay, so now let's see this again. Okay, so now this is basically a compression of this stage. Hang on, I'll answer your question. Okay, so now you are seeing 1 dB compression around at the input of around -5, right? So we can go back and look at what happened to our compression point. So we can go back again, enable this guy and this guy, and put this back again over here, enable this one, okay, and run this again. Okay, this is not there. Let's put here a gain, and let's put here a P out. Okay, so now let's put here a marker. 43.1 is the gain. .1 is over here. Okay, I am roughly delivering 30 dBm. Okay, so this is a good tool to be doing your budgeting. If you design it well, you don't have to do iterations, but you have an option available where you can see how much is the compression on each one and stuff like that, and then you will be able to design it correctly. Okay, so this is your TOI as well. Now, once you have frozen this, once you have frozen a chain, then you can go ahead and start taking these specifications and start implementing the circuit level components. Okay, so what I'm saying is you go from system level, you make sure that you get your delivered power at a given compression, okay, and then you get your specs on each one of them, and then you start doing the circuit design. So that's the whole procedure, right? So that's the whole point of this exercise. So what I'm going to do is we are going to take a 10-minute break, right? And we will meet at 11:05 or 11:10. Okay. Meanwhile, if you have a question, I'll try to answer that question. So all of you can take a break, but if you have a question, you type it over here. Why we take 2-port mixer model while in real life there is a 3-port device? Well, this is a limitation of your tool, the way this budget analysis was written. Okay, this is a limitation of your ADS budget analysis. Okay, so it is not in that that in your real circuit you will not have a 3-port mixer. You will have a 3-port mixer, right? It's just that for my budget analysis, I am not allowed to use 3-port components. So this is a limitation of the budget simulator here, the way they have written it, right? So I hope I have answered your question. Okay, the whole point is you start with the system level, extract the specification of each component. Once you are frozen the system level, then go and design as per the system. From the system, what specifications you get, you go and start designing circuits from that. Now, if the circuit designer comes back and says that he is not able to achieve it, then you will have to go back to your system level and make the changes and see if you have any what you call any margins. Okay, if you have any margins over here, then you can relax the circuit designer. But as a system designer, you always keep margin somewhere, because circuit designers will always come back and say that we can't achieve it, right? So how is to be choosing the best specification for a big question? Okay, no, it is not a big question. It's a small question. The question is, if you go back to my presentation and read it, okay, read it. We started with the output power level, right? So if you see, we started with when you look at the transmitter characteristics, right? I started talking about the output power level over here. I said, find out the worst case. So that starts with the sensitivity of the receiver. Then look at your antenna. What kind of antenna gains are there? What band you are in, that will decide how much attenuation you're going to see. And then the path loss, that basically is your wavelength and the distance you are looking at. So the R is going to be R max in your case. R max is going to be basically edge of the cell, right? For a given wavelength, you choose a certain path loss, okay? Or rather, you will have a certain path loss for a given frequency. For a given cell size, you have a certain path loss, right? And then for that path loss, and also you will have certain attenuation depending on what band you are in. Then you look at your antenna. Does it have an antenna gain? Okay, so you put that number over here. And then the sensitivity part, okay? You put the receiver sensitivity over. So you now have P out max. So if you go back to simulation, you start from the right hand side. You start with the P out max. And then you go ahead and compute TOIs and SOIs. If you have a problem of compression, you're not able to deliver that linear power, then do the budget analysis, find out where is the problem. Once you know the problem, you correct that problem, okay? And once you have frozen this system level chain, then you are going to go to the circuit level. So in a transmitter, what's important is output power and at what linearity. So these are the two most important points. All other things are secondary, okay? For a link, most important is how much output power you're going to put and how much should be the linear power actually. Now, how much linear output power you should put. So that's the question. So now, if we were to start with a back off, right? So I showed you, right? You might have to back off. For a given bit error rate, you might have to back off. So you are designing at a certain linear power, right? So in that way, you have to do the budgeting. So let's say if the 1 dB compression is around 30, that means that let's say if it is Wi-Fi, then I am doing 24 dBm on this chain, which is what is required for a Wi-Fi. Okay, so if you have 802.11 ABG, you have a linear power requirement of, let's say, 24 dBm, let's say. Okay, so now your crest factor for that modulation is 6.7. So 24 plus 6.7, you should be able to do a 1 dB compression at around 31. Okay, same thing, let's say a system requires like 16 dBm out or 19 dBm out linear. Okay, so 19 dBm linear means that the compression for that 802.11, the crest factor is 6.67, right? So add 19 plus 6.67, that should be your 1 dB compression point. And then you do the assessment of TOI 11 dB above and 9 dB above. So this is not a big question. This is a small question. You'd start with what is linear power is required. Okay, again, the linear power basically is coming from here. The linear power is coming from here. So basically, when someone comes up and says that I have to design a Wi-Fi router and I want to cover a distance of like 50 meters or 100 meters. So for 100 meters, okay, you have to design. So in that case, your path loss is fixed. Your attenuation is fixed, right? Then your antenna gains are almost, let's say, isotropic. Okay, so the gain is 0 here. So you have this term going 0. Now you have the sensitivity of the receiver. Now add that, if that comes around something like 19 dBm, that's what commercially people are doing, then your compression point is around 25.7. And then you design for 25.7 compression points. So the TOI is going to be 11 or 12 dB above that. And then SOI would be above that. Okay, PA gain is taking 20 and TOI 14. PA gain is 20 and TOI is 14. Okay, you should understand this. This is a gain, okay, and this is a compression. Gain means it is going to be P out by P in, or P out in dBm minus P in. So that's a gain. Okay, while this has to do with the power level, which is going to be dBm, right? So if it's a TOI of 14, okay, what does it mean? It means that your 1 dB compression point was around 3 dBm. Okay, so TOI is related to the absolute power you are going to do, and gain is something which your transceiver, basically your DSP output, right? So how is the gain decided? So let's say I have a DAC here, which is going to give you an analog output, and that analog output is like minus let's say minus 20 dBm. Okay, I have to deliver 30 over here. So this is minus 20 over here, this is 30 over here. So the overall gain of the chain would be 50. Okay, so power delivered here is 30, gain is 50. So where is the gain computation coming from? I know what is my linear out. Okay, I know what my DAC is doing. Okay, if the DAC is doing minus 20 and I want 30 out, so what would I do? I should have a gain of 50 at least, right? So that's how I would compute gain. So here it is 43. So the gain budgeting is considering what is to be delivered and what the DAC output is going to be. So the remaining stuff is going to be the transmitter gain. So accordingly, you are going to put gain stages, right? And this TOI has to do with the output delivered power. Okay, now this gain you are dividing in different stages. So mixer realistic gain around 8 or 10. Gilbert cell is going to do this. Now, if I was to do a balanced mixer, it will be like minus 8 or minus 7. So in this case, if I want a gain of 40 or 50, then it is minus 8 over here. Then the remaining gain has to come from the gain stages over here, right? So then I'm going to split it up into driver and power stage, or I might need a 3-stage. Okay, so that's how you do it. Okay, you divide the gain over different paths. You decide the output power delivered. From there, you decide what should be the compression points for each one of the stages. So I hope I have answered your question. So I'm going to pause recording. Let's take a break up to 10, 11, 15. So we are going to start with a detector. A detector is nothing but some form of a rectification. Okay, you can represent this just like a diode, right? So you can say that this is some form of a diode, right? And let's do this. Okay, to be, so this is my detector. This is how I represent it. Okay, let this be my detector. Okay, so for a certain bit error rate, so my input is, I have, my system says that I can tolerate a certain bit error rate. Okay. Okay, so for a given bit error rate for this detector, okay, there should be a minimum signal to noise ratio. So for this given bit error rate, signal to noise ratio should be greater than some number. Okay. Okay, so for a certain bit error rate, signal to noise ratio at the detector. So I would put this as bracket. So insert. Okay, so for a certain bit error rate at the detector, I'm expecting certain signal to noise ratio, correct? Now there is a receiver over here which has got gain stages, mixer, LNA. So we will have gain stages here, which are going to be IF gain stages. So let me put here. Okay, so there are going to be a bunch of gain stages over here. So I'm going to represent multiple gain stages like this. Okay, now before that, there's going to be a mixer now. So over here, there would be a mixer. Let me just draw a mixer. Insert shapes mixer. So there's your mixer. Right? And then before that, there will be another gain stage here. Okay, so let's see the significance of each one of them. And then before this, there would be a BPF. This is called the image reject filter. In case it is a heterodyne, or either even in any case, there would be a BPF here. So there would be a band pass filter here. Sorry. Button clicks. Okay. So there's a BPF over here, and then there's going to be an antenna. Fine. So this is right now what typical chain would be like. Correct? Now I start with the signal to noise ratio at the detector, right? Now I have to know what is the signal to noise ratio over here. Okay, so I want to know what this results in signal to noise ratio at the antenna, right? So now these are all cascaded gain stages, right? So how does it go? So there is something called noise figure, which is in dB, and noise factor, which is in pure number. And what is a noise factor? Okay, so insert. Okay, so I will say noise factor is basically gain offered to the noise. So this gain offered to the noise will be so this will be the gain offered to the noise. So output noise divided by the input noise. So this will be noise output divided by the noise input. Right? And then the gain offered to the noise to the gain offered to the signal. Okay? So the gain offered to the signal would be SO and SI. Correct? Now I can rearrange these terms, right? So if I rearrange these terms, I will get signal to noise ratio at the input. Divided by signal to noise ratio at the output. Okay, so that would be the noise factor. So I assume that this number would be 1. Okay, the best case possible is 1. Noise factor is 1. That means in dB, okay, so the noise figure would be in dB, would be 0. Okay, so this NFdB, dB should be equal to 0. Best case is 0 dB, right? And the best case over here should be 1. So this is what I'm expecting, right? The gain offered to the noise is the same as the gain offered to the signal. So noise factor 1. Now, I start with a signal to noise ratio over here. So the overall noise figure, okay, or noise factor for this receiver is going to be signal to noise ratio at the input, which is this, divided by signal to noise ratio over here, right? So basically then this number NF would be signal to noise ratio at the antenna. So this will be that. And let's remove the ideal case. And then this guy. Right? So this is going to be the receiver noise factor, the overall noise factor of the receiver. So basically, signal to noise ratio at the detector is fixed for a given bit error rate. So then what should be the signal to noise ratio at the antenna? It should be basically this multiplied over here. Correct? So at the antenna, I should see this. Okay, so now let us assume that I have only thermal noise at the input. Okay, so this is the simplified version. So that would be equal to, okay, that would be proportional to the Boltzmann constant. Where did it go? Come on. So that will be proportional to the Boltzmann constant KB. And then it will be proportional to the bandwidth, because it is a white noise, so you collect it over an entire bandwidth for which you have designed, right? KB. And then it is a thermal noise, so it has to depend on temperature. Correct? So let's put E multiply sign so that you don't get confused. So that's what this is. This is the thermal noise. So now if I want the signal, so I will multiply this with the noise. Okay. So if I take the noise on the right hand side, So that's the thermal noise. Oh, wow. What happened? Just opened a new one. Okay. Okay. So noise at the input. And that noise, so this will become signal at the antenna. So signal at the antenna should be this much. And this N thing is basically this. Control X. I'll put it over here. Control V. So this is what I'm expecting should be the signal for a given bit error rate, right? Is that clear, right? So what I have done, I'm saying that for a given bit error rate, the antenna should have a signal strength of this much. Now, in terms of voltage, it would be, just 1 second. In terms of voltage, it should be this times of the impedance, which is Z0. Z0. And this would be V, not S. So now you see that this should be the minimum power signal strength, which you should receive for a given bit error rate. So is that clear? So for a given bit error rate, so recording is on, right? For a given bit error rate, I'm supposed to have a signal strength of this. This is also called sensitivity E. Okay, so now the design is very simple. You design, okay, you know that you need a certain bit error rate. Okay, and now you have to construct this guy for a given sensitivity. So basically what is given to you here, you know that this is 50, you know this is ambient temperature, you know that this is the bandwidth of the system bandwidth, this Boltzmann constant is constant, this is already selected for a given bit error rate, you have already selected it. Okay, so everything is basically figured out. Now you have to construct for a given noise figure this chain. Okay, so this is as simple as that. You have to construct a receiver for a given bit error rate, and that means you are constructing for a certain noise figure. Okay, noise factor. So now let's see what is this noise factor going to be. Okay, so I am going to look at this noise factor. Control C, Control V. Okay, so here what I'll do is this would be the loss of this filter. Okay, so this will be BPF loss. So insert, sorry. So this will be L BPF. Right? Now, next, it is going to be the noise factor of this LNA. Noise factor of the LNA. Okay, where would I do that? So I'm dealing with not with noise figure, noise factor of the LNA. Okay. So this is going to be that. And then there will be some contribution from here. So let's say that there are gain stages over here. Let's say there are 3 gain stages here, G1, G2, G3, and so on. Okay. And let's say the detector has a certain, okay, what you will call, not a detector. I would say there is a certain signal to noise ratio over here, right? So, okay. So there is a noise, this has a, let's say this first stage, that is G3. Okay. So G3 has a certain noise figure NF3. Okay. So what will I do? I will do NF3 so this will be NF3 divided by all the previous gains. So this will be G3. Well, you know, Of course, NF3, so there'll be only 2 gain stages over here because this gain is not doing anything, right? So they're only G1 and G2. So there are only 2 gain stages before that. And then there is a factor of 1, which I will subtract from it. Okay. And then I would do G1, G2. G1 and G2. Okay. And then what about the second one? The second one is going to have only G1 in front of it. So G1 in front of it. Okay. And then after the second one, you have a mixer. Okay. So let's say I'm going to put here mixer. Okay. So NFM. And of course, so these will also be divided by GM, gain of a mixer, right? Conversion gain, or GC, I would say. So I'll put here other blocks here. Okay, GC. So I'll keep adding gain. So there is a GC stage here, and there is a GC stage here. Okay, and okay, now the next thing is there is a gain of LNA over here, right? So there will be a GLNA. And there will be a GLNA here. So G2 is gone. So there will be all these G1 and GLNA. Okay, and then there will be a mixer. Okay, it's already there. Here I would have only GLNA, GC, GC, G1. Hang on. This is third one. Okay, this is the second one, and then there is a first one. Okay. Third one. So you can use this for subscript. Okay, understand that. So there is a third stage, and there are going to be second stage, first stage, mixer, LNA. Okay, then this is a second stage, first stage, mixer, LNA. Okay, then there is going to be the first stage, that is going to be mixer, LNA. And then there is going to be mixer, where there will be only LNA. Okay, and this thing is going to be added to this guy. Okay, so this is very clear. Okay, so this is what is happening, right? So if I say, what is the contribution of this guy to the overall noise figure? Nothing, because it is divided by 4 gains. What about this one? It's divided by 3 gains. What about this one? It is divided by 2 gains. What about this one? It is divided by 1 gain. So what matters is, if I have a very large gain of a LNA, then all these terms are useless. I have a very large gain on LNA. Then what is important is, even this term is useless because the gain is very large. So I'm left with only this. Correct? So if you construct this right, if you have a large gain on a LNA, then it is just the noise figure of LNA plus the loss of the BPF. That is going to be your NF, and that will go over here. Okay, so now what's the problem? The problem is the following. If you keep increasing the gain of the LNA, then there is a problem here. How much signal strength can you hit it with? Okay, how much signal strength can you hit it with? So let's say if there is a gain of 20 over here, right? And let's say that I'm going to hit it with 0. And then that means that there will be 20 out here. So what it means is the following. So in this case, the critical thing is, so we know what is the lowest, which is the lowest voltage. So this is 1. This is referring to the lowest voltage, a signal, lowest signal voltage, lowest voltage. Okay, so this we have figured out, and this we have figured out that there has to be NF, and for NF we know that the gain of the LNA should be very large, right? So that the thing over here doesn't matter. But that and very large is not possible because there is another constraint. The other constraint is the distortion or TOI. Okay, and this gap, okay, this gap between voltage and TOI, or sensitivity and TOI, okay, so this gap is called SFDR. Okay, so this gap is called SFDR. Okay, so we are designing for certain dynamic range. The upper value is the TOI. So I would call this as ITOI, not OTOI. Okay, so the upper value is ITOI. So ITOI, and then the sensitivity is the lower value. Okay, this gap is called SFDR. So you are designing for a certain SFDR. Okay, the lowest value is sensitivity, the highest value is ITOI. Now the question is, what is ITOI going to be? Okay, so that starts from here, from ADC. What range of ADC do you want? Okay, from there you can compute what should be the ITOI. So that is going to be the highest power level, right? Okay, so you want to cover the entire dynamic range of ADC. So that is will be LSB and MSB. So basically you have a dynamic range of ADC. That's basically telling you what is the highest signal your ADC can achieve. And then from there, you find out what should be your input TOI. You don't want a distortion to be over here, right? So once we know this, we know that there is certain gain. Okay, so once we know that, we should keep maximum gain on this side, but then you will distribute the gain over here. Okay, now what's the problem putting maximum gain on the LNA? Problem is that the mixer limits the compression point. Okay, so because the mixer, let's say, is again a Gilbert cell. Okay, so it would have a compression point, right? That will be decided by the size of those transistors, as small as possible that you can do. So let's say if you do a very small size of those transistors and you compromise the entire conversion gain, okay, then that would be what your mixer can tolerate. Okay, so now if I was to say that mixer can do 10 dBm out, or let's say 0 dBm out, and the conversion gain is 8, then the input side should be 2. So if this is doing 10, this is 2. Now let's go back to our simulation here. Okay, well, you know, a mixer, let's assume that the mixer is going to be the same as the mixer which we use for this guy. Okay, let's say we are going to use same mixer. Now let's look at this. TOI is around 10, that means it's around 0. So this is compressing around 0. Now if I was to put a gain of 20 here, right? If I was to put a gain of 20 here, then it will be 0 minus 20. So this can go, and then plus this loss. So 0 minus 20, it will be minus 20. Minus 20 plus, let's say, a dB loss in this, minus 19. So in this case, this would saturate at minus 19. Correct? So then in this case, this will be minus 19. not ITOI, it would be compression. So it's minus 19. So ITOI would be around what, 8? Minus 8. Okay. So now this is your SFTR. The sensitivity in the range of around minus 100 to minus 110. And TOI is around this. Okay. Now, if I am assuming that if it is a thermal noise, so this basically is a thermal noise. This is true if this is a thermal noise. What if there is a noisy environment over here? Then in that case, you will not take the thermal noise, but you will take the signal strength here of the noise. Okay. And in most cases, what happens is if the noise is very large, I will not use LNA because the mixer is going to compress. So I am going to throw out LNA. I am going to just use a mixer. That happens in most of the radars. So in radars, you would highly likely that you won't have a LNA. You would directly have a mixer for the dynamic range. Okay, so it's just not the thermal noise. It's basically whatever it picks up here. This is the best scenario. But whatever picks up here, if it is stronger than the thermal noise, then you will assume that over here instead of this. Okay. Now, having said that, in any communication system, there are going to be blockers. Okay. Now, let's say that there is an IF frequency. Okay. So let's say this is a heterodyne. For simplicity, this is a heterodyne and there is an IF here. Okay. And then there is a LO over here, which will be LO over here. Okay. And then there will be RF over here. Usually RF is IF higher than LO, right? So this is a low side injection. So I can write this as this. So when I mix this with this, I get IF. Okay. Now, if I mix this also, if I mix this, how would I say that? Not RF minus, so it will be minus IF. Okay. So if I mix this also, I'll get this. This is the image of that. Okay. So let's say I am working with 27.6 here, and 0.6 is this. So for simplicity, you can understand like this. So this is 0.6 gigahertz, right? And this is 27.6 as an example, right? Whatever we did in up conversion, we are doing the reverse here. Okay, so I'm going to get 0.6 if I mix it with 27. This is called low side injection. So my LO is smaller than the RF frequency. Fine, this is what's going to happen is if I mix it. Now, what about this component? This component is going to be 26 point, sorry. So this component is going to be 26.4. Okay, so now in this system, do you think I have any protection against this frequency? This is undesired frequency. Let's make it red color. Okay, this is undesired frequency. This is called the image. Okay, so I have this image. And do I have any protection? The only protection is this guy. Correct? The only protection is this guy for this image. LNA is going to be broadband enough. It's not going to give a suppression of this frequency. Mixer is going to respond to this as well as this in the same way because mixer is very broadband usually. So both components are going to give me 0.6, right? If I mix with 27. Okay, so the only protection over here is this. Okay, now having said that, is that the whole situation? No, the situation is even worse than that. I'll tell you why. Okay, so let's say I do a pictorial representation. Insert Okay, so this is my desired 27.6. Come on, why can't I change this? Huh. Anyways, and this is my LO, correct? And then the difference of this is going to be IF. Okay, so when I mix this together, so this is LO, this is this, and there is a one which is not desired, which is over here. Okay, and I will dot it. That's the image. So I am going to put a filter around here on this one and reject this one, right? Now, when I mix this, I'm going to get a component which is going to be IF frequency over here. Okay, so again, can I not change this? Okay, and then let me draw a reference to this so that you are not confused. So this is my axis. And just rotate this one. Okay, so I mix this one with this one to get this one. And if I mix this one with this one, I'll also get this one. But next thing I want to do is I want to take another component which is halfway in between them. Okay, so let's say I have a component which is halfway between them. And let's say that this thing is this color. Okay, so I have a filter around it. So let's also put a filter. Okay, so let's say filter does this, and I am going to just do this. And sorry, and that's my filter. Let's say group, group, and just put that filter around there. So let's say I put a filter around here. Okay, I'm going to suppress this guy, maybe LO also. It is centered around here. Okay, so this is your BPF, correct? And this is your LO frequency. So LO doesn't go, LO is not going to go anywhere here. Okay, so now the image is over here. So the image is totally suppressed. Okay, image is totally suppressed. So I'm not going to get any component out of the image here. Okay, everything is the desired one. But look at the yellow one. Yellow is halfway between the two. So what's the frequency of this one? This one is going to be LO plus half IF. This is going to be LO plus half times of IF. Correct? Now, is this component suppressed? Answer is no, because the sharpness of this fall off of BPF was not enough. So this is the component which is not being suppressed, which is suppressed very little. Okay, so now how is it going to hurt me? Let's look at the second harmonic of this. 2 into bracket. If you have a second harmonic of this component, you have a second harmonic. And then let's look at a second harmonic of LO. Okay, so second harmonic of LO is that. Okay, and if I was to mix these two together, what do I get? Let's make this another color. And let's reuse this because it is kind of compressed. I'm going to get back this. So this yellow component, let's make this yellow so that you have. From this component, I'm getting back this component. This is because the skirts of the filter were not sharp enough. And this is a half IF. So this is half IF above LO. Similarly, I can have 1/3 IF above LO. Okay, so somewhere in between here is 1/3, but then 1/3 is suppressed. So 1/3 is not troubling you. What's troubling you is half. So this is called a classic half F problem, right? So basically half F you are not able to suppress by the filter, and that would on the second harmonics, if they mix, that will give me back IF. Okay, so now what's important? What's important for this guy is SOI, because this second harmonic is coming from the even order mixings. The second harmonics are coming from the second order mixing. So if you look at linearity for a PA, you are looking at TOI. But if you are looking for a linearity of a LNA, you are focusing on SOI. Why? Because SOI would give you a half IF problem. Now this is there true for a heterodyne. What about direct conversion? Okay, in direct conversion, you won't see this issue, because in that case, it is already equally bad. Okay, in this, if I was to do, this is basically going to be a heterodyne case. So let's look at what happens under direct conversion case. Okay, so let's look at the direct conversion case. In that case, there is no IF. So that means that RF and LO are on top of each other. Okay, and this results in the baseband, which would be this. And this basically is nothing but this and folded over itself. Where is it? Come on, format. Undo. This folds over itself like this. And let's make it dot so that you can see underneath. Okay, so this is what is happening under direct conversion. This is what is happening under heterodyne, or rather low IF. This is what's happening. That's what you got. You understand what I'm saying? Okay, so half IF problem is there in a heterodyne. Whenever you put IF, there is an issue. There is another issue. Another issue is this has only protection as this BPF. Okay, the other issue is if there is a blocker, okay, which is, let's say, 80 dB more stronger than the signal, for example. Okay, and this is 80 dB. So let's put here. So over here, this is blocked by 80 dB. So let's put here. Okay, so now this is 80 dB lower. So this signal, which came out of the mixer, was blocked by 80. So it was minus 80 dBc. So minus 80 dBc. Okay, so this guy was minus 80 dBc. Correct? Now, I had a blocker at the same frequency. So I had a blocker at this frequency. Okay, now this was being suppressed by 80, but that blocker was 80 dB strong, or rather not 80 dB strong. TOI is over here is minus 8. Okay, so it's 72 dB strong. So this was a 72 dB stronger than the signal. What do you think? Rather, I would put 72 dBm like that. Okay, at this frequency, I had a blocker of 72 dBm. This rejection was 80. What output power am I putting at this frequency is going to be minus 8. Okay, so I will be putting out, the blocker would be putting out a minus 8 over here. So let's make this red color. So the blocker is putting out minus 8 dBm. Okay, what do you think would happen to the receiver? It will compress. this guy would compress this whole receive chain. You are out of the SFDR. Once you are out of the SFDR, you will receive nothing. It's gone. You are jammed. Okay, so the frequency at which you are going to be worse hit is going to be blocker at the image frequency. So SFDR is not counted by then the TO, the sensitivity doesn't come into picture, because what blocker is going to do is it is going to saturate this. So basically, let's forget this number for a second. Okay, let's say that the minimum signal strength I could receive is this sensitivity, and then there is a 80 dB of filtering here. Okay, and the blocker basically can. So what is the lower limit of that? Okay, that would be the attenuation of the filter, not the sensitivity. So basically, what will become important here is the image rejection of the filter. So this is your dynamic range now, not sensitivity. Because the noise, which is blocker, is a noise. Noise is more powerful than what your receiver could receive, right? So it will not see that. It will see the noise, right? It will not see what is the lowest signal I can receive. So if I was to do this in case of presentation, you will see that over here. So if I do a image filter rejection of 85 dB, my sensitivity is over here, but then I am not going to see anything beyond that. This is my filter only which is doing it. I can see only up to what the filter is rejecting if I have a blocker at the image frequency. So you understand the blocker at the image frequency is going to be the worst one. And the only protection you have is the image reject filter. Okay, so I am going to stop here. I hope you can take this idea. You can think about what that filter is doing and what a blocker will do. In absence of a blocker, you can look at a sensitivity, or you can look at the SFDR with lower limited sensitivity. But in presence of a blocker at image frequency, you are looking at the rejection of the filter and the TOI. So you understand that the SFDR is curtailed by a blocker. Okay, so that's the whole idea when you are designing. So I'm going to take a break. We are going to take a lunch break here, and just wrap this thing around your head, what I said. And then we will get on with putting a chain like this. Where did it go? A chain like this. And then we'll do a budget analysis on this. Okay, so it will be just two simulations, one for the compression, other for the budget analysis. And that's it. Then we will jump into modulation schemes. We will make modulators. Okay, so let's take a break of 1.5 hours. Okay, thanks a lot. If you have a question, you can type here. I'm gonna basically stop recording.